Hello, my name is Cooper Zaransky. I'm a computer engineering student at IUPUI Indianapolis, and I lead Dr. Zhang's VR undergraduate research team. The objective of this research is to develop a few educational virtual reality modules for additive manufacturing and multiple 3D printing processes specifically, with the aim of helping students to more easily access, understand, and learn the processes in a more controlled environment. Part of the motivation for doing this is additive manufacturing machines can be dangerous and expensive, and making a VR module to train a user on how to use them or how they operate can negate a lot of those factors, whether it be the inability to leave them unattended, how long it takes to complete a print, or even fire hazards. Our team has developed a virtual reality module as well as an identical mouse and keyboard controlled version in order to improve the learning outcomes of these additive manufacturing techniques and processes. The PC version was created to help mitigate the negative effects some users experience while wearing a VR headset, or sometimes simply not having enough room or access to one. The module I will be demonstrating today is our first and most advanced module we have created thus far. It is a FDM machine that extrudes thermoplastics. The software and hardware used were our IUPUI's own HTC Vive, scripts written in C# using Visual Studio, as well as the Unity 3D game engine. In the module, the user can move around by using the thumb pad on one of the handheld controllers. The position of the thumb on the thumb pad is mapped as a 2D vector into the game, indicating the direction and magnitude at which the player should move. The printer itself is controlled by two monitors with buttons on them, each button containing a script with an overridden method that detects a finger's collision in the game with said button. Then, this method invokes a parent method which executes the desired action based on which button is hit and what its name is used as an input into said method. For example, as you can see, there are buttons to increase and decrease speed, iterate through a list of colors, start printing an object, or iterate through a list of different geometries. As far as the creation of the printed object on the build plate, the nozzle of the printer contains a source for fluid particles to spawn. This creates the illusion of the filament melting and extruding onto the build plate. Then, post-cooling every layer, a .obj CAD model is instantiated where those particles were. Every layer, the layer's color, is matched to the color of the particles. And the way that this creates the illusion of an actual printed multi-layer object is how every layer is a different CAD model, but they are all parented by a container. This container will then receive the common behavior, such as properties that dictate how it interacts with physics and how the user can interact with it, as well as acting like one solid when it is picked up and rotated. As an example here, there is an ASTM D638 Type 4 tensile bar. The motion of the printer is emulated by a single script that describes the kinematic behavior of the printer. It contains many different compartmentalized and abstracted methods to create that illusion so that it can be reused to create different shapes. In Unity 3D, the center of the bed plate is defined as coordinate 0, 0, 0. Now, this is done so that as the bed plate lowers, it continues to be able to be fed different coordinates and speeds, which it can then process and linearly interpolate between to create moves between the current and the next point, changing the position once per frame, usually on a VR headset running around 60 to 90 frames per second. Now, each frame, the position is processed via different dynamic methods, and it will also animate all belts and pulleys as a function of the printhead's current XY position. This way, it is not hard-coded for different shapes. The printer we have chosen to model uses the Core XY Cartesian motion system. The graphic on the left is provided by Core XY's original inventor at their official website. The equations on the right were derived by our team to recreate this illusion of system motion within the confines of the 3D printer model in the game. In order to enhance a realistic feel for the user, inside the module, the setting is a laboratory. The user can switch filament colors, and the user can physically handle the object after it's printed, taking it off the build plate. Demonstrated here is another shape we have provided, the cylinder. On the left, you'll see the very first layer, and on the right, you will see after the head has returned to its home position and the bed plate has lowered all the way, yielding the finished product. This is a screenshot from the PC mouse and keyboard version of the module, and as you can see, it looks exactly identical. I'll now show a short demonstration. As you can see, all idlers are rotating and belts provide the illusion of motion. After multiple layers and multiple filament changes, you can see the progress of the object. Then, after completion, it returns. The user can then reach and pick up the object off the build plate. In conclusion, we have successfully created educational modules in virtual reality of an FDM printing machine as well as a PC-controlled version. The gimmick appeal of VR should not be immediately discounted, as keeping a pupil engaged is still a large challenge in education. Though this module still has room to improve before it is as or more effective than demonstration on a real machine, such as future plans to allow the user to run stress tests on printed objects, such as the tensile bar, or interactive labeling of each mechanical component of the printer. Thank you.